Hello, so thank you Sarah for the introduction. Basically today's class will be about vision language models and how they can be used in human-robot interaction. So first I will do a brief introduction of myself. So basically before I started my PhD here, I was studying engineering at the University of Patras, where I spent 2 years working on as a student researcher in robot learning with Professor Konstantinos Hatziligeriudis. And I also spent some time in Ragdoll Dynamics, which basically is a company that builds an animation plugin, where basically they leverage whatever we know from robotics and simulation to improve the life of animators per se. So basically in the previous class, we more or less understood why LLMs are awesome, totally unbiased opinion. But the thing is that when we want to use the LLMs in robotics, I think, and I think you would all agree with me, that language on its own is not enough. And why is it not enough? Because basically we need also vision, and being inspired of how us humans work and think. Basically, let's take as an example me being in my office and I spilled my cup of coffee by accident, okay? I would first think of, oh, I go grab a sponge from the kitchen to clean the mess up. But if I see that I have a towel next to me, of course I will use the towel. I will not go to the kitchen to get a sponge and then go back. And basically this was work by Google done in 2022 that basically showed this. They had the LLM to first plan, and then they used a model to bias these probabilities of selecting the next action by vision. So something else we humans do when we want to interact with robots or among each other, we basically use gestures. So I can tell any one of you, please fetch me that, put it there, bring me this, bring me that. So if you type to an LLM, bring me that, it will most likely tell you, what is that? What are you referring to? So yet again, we need vision context. Also, vision helps with the contextual disambiguation. So for example, as you can see in this image, basically there are 2-3 men in the group, but I'm referring to the one at the left of the screen. So the vision comes to complement my language instruction. And something else that is very, very nice with these kind of models is that they have zero-shot generalization. Why? They are scaled on internet scale data. There is a lot of text data, also a lot of image data on the web that we can use to train these models. So we will do a very, very quick history of overview of vision language alignment. And we will start by this work from Google in 2015. That was a pre-transformer era. And basically in this approach, they used the CNN traditionally to do a feature extraction of images, and these features were then passed into an LSTM to generate captions for images. And as you can see here, it was very groundbreaking for the time. You can have very nice captions. Then sometimes there were minor errors, especially when it comes to counting. And also when it failed, as you can see here, it's not that wrong, that the concept is okay. There is a dog in the image, but there's no frisbee, there's nothing to catch, etc. So then we move in the modern era of transformers, and we'll start with CLIP. So CLIP is a model that uses 2 encoders, one that is responsible for encoding text and one that is responsible for encoding image. So the text encoder is just an encoder-only transformer, and for the image they used a ResNet-like architecture, like a CNN or a vision transformer. And basically what they did is to project these 2 embeddings into the same shared latent space. And basically the training process was, we had a bunch of image and caption pairs, and the output is a cosine similarity between all the image vectors and all the labels in the batch. And the objective of the loss function, of course, was to modify the weights of the model such that the correct caption corresponds to each image and vice versa, okay? So how does this look like, and why is it called a contrastive loss? Basically, we have 2 terms, and the first term is maximizing the similarity score between an image and its correct text caption, while also minimizing the score against all the other pairs, hence contrastive. So we maximize the the similar ones and we minimize the non-similar ones, okay? And the second term is doing exactly the same, but for the similarity score between the text and its correct image. So let's take a look at the numerators. So here is the similarity score, as we said, of the correct matching pair image I and text T. And tau is a scalar value that is learned, and it basically affects the slope and the sharpness of the probability of matching or non-matching the pairs. And in the denominators, you can see that in the first term, we have the similarity between an image I and every text in the batch J. And the sum of these basically represents the competition the correct text must beat, okay? And on the second term, it's exactly the same, but for the image J and all the, the text I and all the other images J. So, what can clip models do? As you can see here, the basic example is we have a bunch of labels, plane, car, dog, bird, and we pass this batch to the text encoder, and we give our target image. And basically, we calculate the similarity score among the two embeddings, and the highest one is the one that wins. And in this case, we have a photo of a dog. But we can also use clip-like models for other applications. So we could potentially split an image into patches, pass these patches into our vision encoder, get the embeddings, and then pass our own text that we want to find in the image. So if I want to classify all the dogs in the image, to detect the dogs in the image, I pass this. I pass all the patches, I find the neighbors, the biggest neighborhood with the highest score has a dog, I create a bounding box, for example. Or we could potentially use them to do image search or reverse image search. So let's assume we have a database of a lot of images, and for each image we have calculated the embedding vector. Then for every text that we pass, we can get the n nearest neighbors of this embedding, or we can pass an image and do exactly the same. So, of course, clip is very cool, but the problem is that it's good at only retrieving and understanding, but it cannot generate text. And the next approach after this was blip, which basically was a unified architecture that did everything that clip could do, but more. So basically, it had a unimodal encoder which was responsible for image-text contrastive layering, similar to clip. Then they had the image-grounded text encoder, which was doing image-text matching, and at the end you had the image-grounded text decoder, which was generating text. So I will do a quick reminder of how an LLM works now before we jump to VLMs, but I suppose most of you already know. So we have a prompt, which will then be tokenized. So these tokens are then used in a lookup table to get the corresponding embeddings, which are then passed into the LLM, and the new token ID is generated. This token will be then appended into our initial prompt, and then we continue this process recursively up until either the stop token just gets generated, which is a special kind of token, which means that our generation process is ready, or if we reach the maximum number of tokens that we ask the LLM to produce. So how most VLMs work. So we take the powerful LLM that we already have, and now we want to add also images into it. So we need our image, then we have a vision encoder and an MLP projector. So we can now ask the LLM, what is this cat doing, and append an image of a cat next to it. And then the vision encoder will basically give us a features vector for this image. And then the MLP projector can map both semantically and dimension-wise the feature vector to the embedding space of the LLM, okay? And as previously, we can get the correct answer, which is the cat is sleeping. So now we can take a look of a few examples of VLMs of this nature. And I chose some specific ones, and you will see why soon. So first we have Polygemma. It's a 3 billion parameter VLM, which uses CGLIP as its vision encoder, which is an improved version of CLIP with a different kind of loss function. And the fun fact about Polygemma is that it's the vision language backbone for Pi0 and Pi05. So basically, I suppose most of you already know this kind of models. The vision language backbone is exactly this model, okay? Then we have Lava, which is very well known, and you can see CLIP that we saw previously is used this time as the vision transformer to get our nice embeddings for vision, and then for the language backbone they are using Llama. Then, since this kind of approaches became very popular, Toyota Research Institute launched a very nice code base accompanied by a paper for trying to, let's say, easily create this kind of VLMs. So you can choose which are the trainable parameters, which are the frozen parameters, what kind of visual representation to use. You want clip, you want siglip, you want dino, you want both, so you can choose whatever you want. And then which language model you want to use as your backbone, what data set, and so on. So it's an easy way to build your own VLM. And if you're lucky enough to have the compute to do this, maybe you should try. And a fun fact about Prismatic VLM is that OpenVLA uses Prismatic VLM as its backbone. They chose siglip and dino plus llama 2. So basically they took this, they did a nice trick in tokenization, and then they had a VLA, okay? So, we can all agree that VLAs are cool. They have really mastered how us humans communicate and perceive. And the question is, where and how can we use them in robotics? So, it was a kind of question I was asking myself when I started my PhD. So, basically, I like to refer to this problem as the HRI communication gap, where basically you can see this lady is asking Talos to move a box onto that table, but Talos is confused because Talos only understands torque or position commands on his joints. He does not understand language. And let's assume Talos is doing a task and is doing a motion to the human, but the human cannot understand Talos because Talos has weird fingers. He also does not have eyes and he does not have a voice. So this is, let's say, the communication gap between humans and robots, and to put it in way simpler terms, robots do not understand humans and humans do not understand robots. So there are two schools for bridging this gap in the new modern era of foundation models. The first one being leveraging pre-trained models to plan, act, predict key points, or to instruct robots, or slightly fine-tune them. Namely LLM Planner, basically generating plans, high-level plans, of pre-known primitives to instruct the robot, inner monologue, RoboPoint, and so on. And the second approach is to either fine-tune or train big models to directly control robots, like the Robotic Transformer 2, the Gemini Robotics VLA, OpenVLA, Flower VLA, and so on. So for the second category of models, there will be a class tomorrow by Professor Lyutitkov, so I will leave the stage to him for those. And today we're going to speak about the first family of models and approaches. So, let's go back to our core problem. Robots do not understand humans, and we'll start speaking about this first. So, what can robots understand? So, I hope most of you are familiar with this kind of schema here. So, robots can understand joint commands, and how can we get them? We can get them through good old-fashioned whole body control, modified as a quadratic program problem. So, we have our cost function, which basically is the tasks that we want to do. For example, we want the right arm of the robot to be somewhere here, the left somewhere here. And typically, these are given through teleoperation interfaces. And sometimes we do want to teleoperate the robot. We don't want it to be autonomous, okay? And this basically task is subject to specific constraints. So, namely, it can be the dynamics, it should be actually the dynamics of the system, the joint limits of the robot, self-collision avoidance, so not colliding with itself, or external collision avoidance, okay? So, as far as external collision avoidance is concerned, usually these are predefined by a very well-known model of the environment. But in the real world, as you may know, environments change all the time, or we may want to deploy the robot in an unknown environment. And the rest of the constraints are typically known from the robot's model. So, let's assume we can and we want to teleoperate the robot, but we want an autonomous way to have external collision avoidance. Basically, this is what we did in this work. You can scan the QR code if you want to find the paper, where basically we leverage the capabilities of large language and vision language models to generate collision avoidance constraints. So, this is an overview of our pipeline. So basically, we have the teleoperator who holds two VR controllers and is equipped with a microphone like me right now. And then after his instructions get transcribed, things pass through our speech-based 3D segmentation pipeline. This is basically generating some segmented point clouds, which are then converted to meshes, and by the meshes you can easily mathematically define the constraints for our QP. So the robot, as you can see, that we use is the bimanual Tiago++ that we equipped with the depth camera. Okay. So the question is how? How can we do this? So as you may know, typically we interact with LLMs by giving a prompt or a user instruction. So basically I can start by asking my LLM, hey, please don't collide with this box, that box, and that table. The LLM will generate nonsense most likely because it doesn't have context for this. Here comes the system prompt to play its role. Basically the system prompt is a set of instructions in natural language that define the task, give more context, give instructions, and so on. So basically in this particular case, the system prompt was something like, okay, you are a system that's helping me with identifying what objects I should not collide with. The human may speak in any language they want, and your role is to return a JSON object that has these tags, and in each tag I expect this kind of values, okay? Is this enough? No. Because as was mentioned in the previous lecture, basically we need more context. And the best way to have in-context learning is to have a few-shot prompting, which is a technique basically where you append to your input a few example input and output pairs. So if my input is something like this, I'm expecting this response. And this has been proven in the literature to really assist with generating nice structured results. So these two, we can hope that these two are enough for us to generate a structured output. And why do we need a structured output? Because we can then parse it and use it in a way we want when we write our code. And the output is something like this, as I described previously. We have the chain of thought. In the previous class, we spent a lot of time understanding why chain of thought is important, so I will not repeat. Then the amount of the list of objects that we want to add into our collision avoidance stack, and the object that I want to remove from my collision avoidance stack. Why? Because assume I'm teleoperating a robot where I want to grasp something behind my laptop, okay? In the beginning, I don't want to collide with my laptop. Okay, I take the object, so whatever, but then I want to close the lid of my laptop. So obviously I want to remove this constraint and update things on the fly, okay? So typically in long horizon tasks, something in the beginning is a collision and in the end it is not. So we can hope that these two things are enough to generate this structured output. But why hope when we can change and manipulate the output of the LLM into something that we want? So there is a technique called logit biasing, where basically you create logit biasing on its own is manipulating the logits, so the probabilities of the next token that we're going to sample, okay? And we can create an FSM, a finite state machine, that defines the structure of our output. So if you did some introduction to programming classes in university, when we did parsing, we're defining some formal grammars that were basically describing the grammar and the structure of the programming language per se. So I know for a fact that when I want a JSON object, the first token I want to see is a curly bracket, okay? Why gamble and not just sample this? So what this technique is doing basically, it has the FSM, and based on the state, it's masking to -infinity the probability of the tokens that are not relevant to the grammar, and is leaving untouched the other probabilities. If we want to bias the model even more, we can add a positive bias to other kind of logits, but this is not relevant in this case. Then we have our ID. Also the IDs are known, so I want to sample this specific ID. And then, for example, I might want a string, which means everything that's not a string will go to -infinity. So by building this FSM, in the end, we can have very nice structured outputs. And I don't know if you've used the API calls for OpenAI, Gemini, and whatnot. Sometimes they give you the JSON schema mode. What's going on under the hood, I suspect, is this. Okay, I'm not sure, but I think it's this. So cool, now we have our structured output. What can we do with it? So we have also our image, and basically we can use the list of objects to get bounding boxes using Grounding Dino. Grounding Dino is a foundation model that generates bounding boxes based on a language tag that we give. And you can see that it performs quite well. The cyan boxes are what I got from Grounding Dino. Of course, previously I told you that you could use clip to do these kind of things. I tried, the grounding dyno was better because it was trained to do exactly this. And then what can we do is pass our image and this bounding box to SAM2. SAM2 is a segment anything model by Meta, where basically it can operate in 3 modes if I recall correctly. One is we give an image and it returns back all the segmentation masks. Or we can provide a prompt by providing a bounding box and the image, so it will give us the segmentation mask of the thing in the bounding box, or by key pointing. So we give a point and it gives the segmentation mask of what I'm pointing in right now. Of course, these 2 things can be replaced by SAM3 now, but when I did this work, SAM3 did not exist. So the thing is that it's not the tool that we're using per se. The way this field works, evolves, we can have something better tomorrow. We don't know. But this pipeline will stay. So even if we have a new model that we can do all of this at once, the core concept of the pipeline can last and we can still use it. So then, basically from the segmentation mask in the image, we get the segmented depth aligned point cloud. And from this, we can downsample it because it might be noisy. And from this downsampled point cloud, we can define a mesh, which can then give us our nice collision avoidance constraints. So in the next video I have audio, I don't know if we can hear it.
Agrega la mesa, la caja verde, la caja negra y el taladro.
So for those of you that don't speak Spanish, Clemente said add the black box, the green box and the drill into the collision avoidance stack.
Agrega la mesa, la caja verde, la caja negra y el taladro.
So on the left, you can see the real-time teleoperation with collision avoidance on, not real-time, times 5 actually. And on the right, we resend exactly the same commands that the teleoperator was sending to see if in the end he actually avoided having collision. So as you will see soon, basically by sending exactly the same commands but with the collision avoidance off, we can notice if it actually helped. So here you can see there was a moment of collision, and we did a quick pilot study in our lab with 5 participants, of whom 4 had never teleoperated a robot before. And basically we told them, okay, you can interact with the robot in any language you want. The task is for it to not collide with specific object, no more instructions, just freely use this and no more context. And 4 out of 5 actually managed to leverage from the capabilities of our system. So our first participant used Arabic, second used French, third used French, fourth Italian, and the fifth everything, basically.
Successfully identified all specified objects, and no collisions occurred during live trials. When the recorded commands were replayed without collision avoidance, collisions occurred in 4 out of 5 trials, demonstrating the effectiveness of the collision avoidance module.
Okay, sorry. Okay, so what happens in the case where we do need autonomy? Okay, teleoperation is nice, we can use it to collect data, we can use it to teleoperate our robots in high-stake scenarios, but as far as human-robot interaction is concerned, there are some cases that we need to speak to the robot and we need the robot to understand us and act based on that. And an example of this is face-to-face human-robot interaction when we do a collaborative task, okay? And basically, a good example of where we could use this is multi-contact motions, because as you may know, humanoids have a human-like structure, and since they are human-like, they can do human-like motions. So as I may lean against a surface to maintain my balance, to improve and increase my reachability, so can a humanoid robot. So traditionally, there are 2 approaches this can be done. The first being contact planning. But as we said previously, contact planning needs, for the external collisions basically, needs a predefined quasi-perfect model of the environment and some pre-programmed, very well-defined and tuned cost functions to select for the contact selection criteria. Another approach is human-guided contact placement through teleoperation. As we said previously, teleoperation is quite nice. But if I want to engage with a robot, speak with a robot, work with a robot, I cannot teleoperate it at the same time. This defeats completely the purpose. So ideally what I want to do is speak to the robot as I would do with any one of you and say, hey, place your right hand there and then fetch me that, okay? And we can do this, and we did this 2 years ago, by leveraging the capabilities of large language and vision language models. And this gives us the ability to be general in any instruction, anything. We don't need a 3D model for the environment, and it completely understands the instructions of the human, okay? So here's our paper called Words to Contact. It was published at Humanoids, I made a mistake here, in 2024. And the paper is at the top right if you want to scan it. Basically, how did we connect language to contacts without training, without any fine-tuning, without nothing, okay? So at the high level, we have our input, which is the image and the user prompt. And then we use a VLM to project the vision to the LLM space, but not in the learning way, as I showed you previously. We use the VLM to generate a text description of the image, okay? Then we include our few-shot prompting techniques and our formal grammar, which defines the constraint I previously explained to you. And in the end, we have our low-level controller, who is responsible for whole body control and retargeting for multi-contact tasks, and we can then control the robot. So let's take a better look of how these things are working in the end. So here's the point of view of Talos. You can see we have a table, we have a mallet, we have a screwdriver, and a box of screws. And the user said, in this case, place your right hand right from the thing with the wooden handle. They did not say mallet, they did not say hammer, they said the thing with the wooden handle. I know today this is not very impressive because we are all used to LLMs and VLMs, but back then it was quite cool. So yeah, what happens next? The VLM will basically give us the bounding box of the thing with the wooden handle. And by the bounding box, we can create it basically, we can create a string that says the thing with the wooden handle is at this position with this width and this height, okay? And then the system prompt is a minimized version of it. Actually, it's not the real one we used, but you can find it on GitHub if you want. Is basically, you need to generate a JSON. Your goal is to define the arithmetic expression that expresses this, defines this displacement, and why arithmetic expression and not do the math completely, because you know that LLMs sometimes are not good at math, and they are not supposed, in my opinion, to be good at math, but they are very good into converting one form of language into another form of language. So if I describe a mathematical expression, if the LLM itself describes a mathematical expression, it can then give me this expression, and I can use a simple Python parser to parse this expression and calculate my point, okay? So with small models, which we're going to use also today for the tutorial, spoiler alert, this is very useful, okay? So this is an example output. So the task is to put the thing there, it's located there, so I need to do an x-axis offset of this and the y-axis offset of that, which will then give us the arithmetic expression that I described previously, okay? So we make the assumption that we have three types of instructions. The first one being the prediction, the initial instruction basically, which will activate the corresponding module. So this module, the prediction module, is responsible for predicting the initial point. As you can see, for the module selection, we used an LLM to classify what kind of instruction we got. And after this, we get, as I showed previously, a point in pixel space that describes the instruction that the human gave. But what happens if we're not satisfied with this prediction? We can ask our system to correct it. So yeah, here we just said move more to the right. It moved more to the right. We could also give way more complex instructions, but I will show you later on. And once we're satisfied with this prediction, we can just let the robot know, and it will activate the control module, which will then control the robot, okay? So, as you can see here in this video,
using your right hand, lean on top of the white surface. Reach for the plate with your left hand.
So you can see the predictions at the top left. The instruction was not given with speech at the time. We typed it on the keyboard. Google Slides is not collaborating today. So the question is now, how does the correction module work? It's actually exactly the same as as the prediction module, with the only difference that the chain of thought is a bit more different. So it defines the task as you need to offset a given point based on a previous prediction. So we need to provide the context of what the current contact point is, of course, and the chat history, because basically through this recursive I speak, the robot predicts, maybe I want to give a correction in a sense, no, twice as much as before, or go to the previous contact point that you were. So the more context we give, the better, most of the times, okay? So here you can see an example of this correction module being utilized.
With the wooden handle.
So yeah, you can see that the first point we got was right next to the thing with the wooden handle. And in order to avoid collision, we really need to move this point a bit far away. So we prompted the system again to move more to the right. We are satisfied, we said, yeah, move on. And then we can ask the robot to reach for the nail box that initially was out of reach. So we did a pilot study with 11 participants for this. Basically, we split the pilot study in two phases. The first phase was we let the system, people interact with the system on their own without giving any context whatsoever. And in the second phase, we gave them instructions of what the system expects, what's the goal of the system, etc. And to basically give you an idea of how the experiment was designed, basically we had a big data set of images that I collected to also evaluate the individual components of the model. And we would randomly select a point in that scene. And we were telling the participants that your goal is to instruct the system to reach to that point, okay? Which is a funny way to design the experiment, to have gamification, because gamification is very important when you do experiments with human participants, because you want them to be engaged. You want them to feel the need to perform well in accomplishing the task, so that you have high quality data to analyze. But also you don't want them to be bored, because we need to think as researchers when we design these kind of experiments, would I enjoy this while I'm doing it? Will I have fun while I do this kind of experiment, okay? So, as you can see in the first phase, there was a downward curve in convergence. Basically, this plot is showing you the number of interactions on the axis of distance in terms of pixels. And when we described to the participants that they can also give corrections, because most of them did not understand that they can correct the point. Or you can give instructions related to other objects and so on. You can see that they all converged, and with a number of 5 steps they were able to reach very near, if not bullseye on the target. Okay. So let's assume we mostly covered the first part, that robots do not understand humans, and let's talk a bit about the fact that humans do not understand robots. And in my personal opinion, transparency and trust are very important when it comes to human-robot interaction. And because most of you, if not all of you, I hope all of you, have used an LLM in the past. And you see that at the bottom there's a disclaimer that it can make mistakes. You should not completely trust it for important things. So when we try to deploy this on the robot, we need to know what's going to happen before it happens. Because if ChatGPT or Gemini or Claude or Mistral gives you a code that is not working, you don't care. You can prompt it again. At the end of the day, nothing bad happened. But if the robot makes a mistake, we might either break the robot or hurt someone. So we really need to know what will happen before it happens. So we can spend all the time in the world to focus on how to make things not fail, but we can also try to do things to anticipate failure and to correct before it happens, okay? So how can a robot typically communicate intent? So as you can see on the left, we have ICAB that had a very nice head with very nice eyes, which allowed people to use gaze as a show of as a mean, of showing intent. And modern robots, I don't know if you've noticed, they either have 2 DOFs, 2 degrees of freedom in their head, or 0. So I don't know if gaze can be used this much in 2026. And another approach is pointing through, as we do, using the robot's arm to point that this, that, there, that. And another mode that we can use now is speech or a combination of both to improve basically engagement for the human. And here's my hot take. My hot take is that robots should not necessarily be human-like, but they should be human understandable. So instead of trying to imitate what humans are doing, we could just do something that humans can understand. So in this work, which is an extension of the previous work I showed you, we basically added a 2 degree of freedom laser on the robot, and the robot uses the laser to point, okay? It's that simple. Because before, in the previous paper that I presented to you, basically the prediction was displayed to the user through a screen. So if you have a screen and the robot, you can just tap on the screen, you know? You don't need all this complicated approach to have a multi-contact with a language. So what we also noticed in the previous work was that people really tended to prefer metric measurements to give corrections. So they were reasoning in meters, in centimeters, inches, whatever. So, and also in the previous work, since we worked on pixel space, we made the assumption that the contact surface is parallel to the point of view of the perpendicular, actually, to the point of view of the camera. So these assumptions are nice to have an initial work, but when we want to improve things, we need to move to 3D. Like for me, pixel space is not enough. And basically, here I have an example of in which kind of scenarios we really want this intent. So basically here you can see we have a glass. So we have a glass, a wine glass, and we have this gray box that you can see here. And we want the robot to support its weight against this gray box and then fetch us the Coke can. So I prompted the robot through speech this time, to Talos, to basically place its right hand like 7 centimeters behind the wine glass. And then Talos... So it's that simple. The robot showed me where the system predicted the key point to be. And since I was sure that it would not collide with the wine glass, I prompted again my system to proceed. And now, since I have a point that Talos can balance, I can ask it to fetch the Coke can. Okay. So, how do we move from pixel space to physical space? So, first of all, we have the intent extraction. And this time, instead of just using a large language model, we back then had VLMs also available. So we also appended the point of view in the intent extraction phase. And this helps with what I mentioned in the beginning of the presentation. Now the VLM can understand that this thing refers to the mustard. And also, since we are doing contact placement, we need to know what the contact surface is. And by providing vision context to the VLM, this can be implied. So the user doesn't have necessarily to explain what the contact surface is, okay? As you can see here, the response again has a chain of thought, which end effector will be used right or left hand. If the task is a contact or a grasp, what is the contact surface, which object was specified, and if the user has confirmed. So here you can see this output is then used by our 3D segmentation module, where basically we do a similar approach as what I showed you previously for the objects in the scene to get their 3D bounding boxes this time. And for the contact planes, we do again the segmentation, but this time we do a plane fitting. So with traditional ransack. So we have the segmented point cloud, we fit a plane, and we can use this plane in the next phase that I can show you now. Where basically we do the spatial reasoning similarly to before, but this time 3D space. But there is a chance that this module will predict a contact point that's in the air. But I don't want to make contact in the air. And since my mean of communicating where this contact point is a laser, I don't want air, I want the surface. And if I point in the air, it will end up in a surface. So it's not what I necessarily need. So for two reasons, we project this predicted contact point into the surface that we previously identified. As far as expression is concerned, basically we pass all the previous reasoning traces from the previous models into an LLM. And we ask in the system prompt, we specify that the goal is to now generate a human-like response, a natural response based on does this point look good, should I proceed, and so on. But also, if in the reasoning traces there is something wrong, it should verbalize and communicate this to the human. Like for example, if the image we initially included was basically there was a sign in the contact surface that was saying, oh, please do not touch this surface, then this trace will go back into this LLM that will verbalize to the human, hey, I don't think I'm supposed to touch the surface, and I did some preliminary experiments in the lab and it worked. And then for the pointing device, basically we know where a point is in the world, and we know where the laser is in the world because we know where we attached it on the robot. So from the forward kinematics, we know where everything is. So how can I point? Basically, this is called the look-at transformation that is used a lot in computer graphics and vision. So basically, you just connect the two lines. So you have your first axis of your frame. Then you define a pseudo frame to define the third frame that will then give you the second frame that will then give you the third frame. So it's just some very simple linear algebra that you can look up, and basically you can use this to point to specific points in the world. So how did we control our robot? So for Tiago, we used our OpenStack of Tasks, which is a library that is maintained in the lab and developed by a permanent researcher in our lab. And basically, for Tiago specifically, we in the non-user confirmed phase, we also added the support for pointing with a hand, and not just with a laser, because as I will show you in the next slide, we did a very big user study with this. And once the user confirmed, we would go in our target and do the task that was necessary. So the user study consisted of 15 participants, and we had two modalities. So it was a within user study. So each user would control the robot in two modalities, laser and pointing, in two different setups. So we had the tabletop setup and the industrial setup. So they would randomly get assigned with what modality they start, which setup they start, and so on, to try to remove biases. So if they started first with the hand and then with the pointing, they would be, oh, this is so much better, or I don't know. So to remove biases, you need to shuffle and try to randomize the things. And for gamification, again, which I told you is important, we added 5 targets in the scene, and the goal was to try to reach these targets with the robot this time. So in the tabletop setup, they had to drop a ball in one of these targets, and in the industrial setup, they had to poke with the robot on this target, and for each target they reached, they would get a point, and there was a leaderboard. So everyone got a bit competitive, they wanted to be behind the leaderboard, so we were very engaged into fulfilling the task. And as you can see, it took 1 or 2 hours per participant. So if you do the multiplication, you can see that it took a lot of time to do this user study. And why did we do this user study? Because maybe in my head it is obvious that, yeah, of course the laser is going to be better, but obvious is not enough in papers. So you can see here, the two modalities being compared. So top, you have the pointing with the hand, especially on the left because on the right is not that visible. And bottom, you have the laser. So you can see that the laser is moving as the human is correcting. And once the human is happy, they confirm. And the task of poking looks like this. The task of dropping looks like this. So yeah. Is the laser actually better? So here we compare the subjective measures. We did a NASA TLX, and basically you can see that overall in most of the axes, the laser outperformed the hand pointing. The only axis that they are on par, and actually the laser is a bit worse, is on the temporal demand. So the question was, did you feel rushed? On a scale from 1 to 7, how rushed did you feel while doing the experiment? So when the laser was used, they felt a bit more rushed, which will be explained later by some subjective measures. Yeah. So here is the system usability scale. Basically, it's a predefined questionnaire of 10 items that gives you a score of how usable your system is. And as you can see, the laser is statistically significant, better than the hand pointing. So here we can see different kind of measurements. So first, let's take a look at this. This is similar to the previous plot that you saw, where you compare the distance to the target based on the interaction, across the interaction, sorry. So we had up to 4 interactions with an extra one used for confirmation if needed. And what is very interesting, apart from the fact that the hand pointing is not converging at all, is that in the laser pointing, the first instruction is very random. So I think that the participants exploited the fact that they can start from a point that they know where it is and then give corrections based on that point. And something else that is very, very interesting is that they tended to confirm later using the laser, because when it's very clear where you are, you know if you are hitting the target or not. So they would use all of their steps, let's say, to reach the target. So maybe I should have added a penalty term for the interactions, but yeah. You can see that, of course, when they confirm or when they correct, they are closer to the target with the laser compared to the hand. And here is what I previously told you, that the participants felt a bit rushed when they did the laser modality, because they were much faster, in fact. The time we measured was from once the pointing was completed, either with the hand or the laser, to the start of the user instruction. And as you can see, they were much, much faster when the laser modality was on, because it was very clear where the system had predicted the key point to be. And I actually noticed while I was doing the experiments that almost all the participants were trying to align with the hand of the robot, check where the vector is going to. So this would add up time and they would be more slower interacting with the system. So yeah. Now for Talos, we use again the whole body controller that I told you before. And this time, and again, we have a cubic spline. We generate the cubic spline from the current and effector position to the contact surface. And since now we have a plane, we are in 3D space, we can automatically get the normal vector, the contact normal vector from the surface, which means we don't have to pre-program that the contact should be on this axis, on that axis, or whatever axis you had before. So we get for free any kind of contact surface we want by just using pure geometry. So as you can see here, before we had putting the hand on top of the gray box. Here we are using a different kind of surface, which is the whiteboard. And I don't know if it's very visible, but the first prediction was somewhere here. I don't know if yep, so here. Then I corrected Talos to go a bit up and the left or right, I don't remember. So it's exactly the same system as before, nothing changed. And now it can support its weight on any kind of surface, as I previously mentioned. So then we can reach for the cup. Sorry that the video is blurred, but the paper is currently under submission, so I anonymized everything. So yeah, the works I presented are not only me, there is a big team behind everything. So I would like to thank my two supervisors, Serena Ivaldi and Jean-Baptiste Mouret. I would also like to help Enrico Mingo Hoffman for his help and consultancy as far as OpenSOT is concerned. I would also like to thank Quentin, who is here today and tomorrow will do a flow matching course for you. Clemente, an engineer that helped me with the experiments with Thiago a lot. And I would really like to help also Romain and Etienne, the two Enact engineers that helped me with all this Docker madness that we did last week, because we wanted to avoid the "it works on my machine" kind of concept. It may not work on anyone's machine, but we will be together in this. We will see later today. So I would also like to thank Thiago Pro, Thiago++, and Talos. So see you in the tutorial number 2, where basically you will learn how to do almost everything we said today as far as VLMs are concerned to interact with Richie Mini. So we will have our own interactive robot and expressive robot if everything goes well. And thank you. Feel free to ask me any questions you want.